This video is about applications of logarithms. The first formula, one of two formulas we're going to talk about, is this one. It's called the interest compounded periodically formula. So whenever you have interest compounded periodically meaning not all the time, like so many times a year. Or it might mean so many times every other year. Maybe bi-yearly or whatever. But generally it's like yearly or monthly or weekly compounded. So in this formula is equal to A equals a P, parentheses 1 plus R divided by N, parentheses N, T. Let's talk about all those letters mean. A is your final amount. P is your initial amount. Initial meaning being beginning amount. Next letter is R. R is your rate. N is your number of times a year. And T is time in years. So T is time in years. It's pretty much all what all the letters be. So, and 1 is just what 1 is. And this rate should be written as a decimal. They may give you a rate as a percentage. If it's a percentage, you should always change that percent to a decimal before you go back into the formula. All right, and let's go put that formula to use. You may want to copy all this down as a note so you know what these letters refer to when we go into other examples. But I'm about to erase this and give you your first example. Here's the example. You invest $7,000 in an account bearing 5% interest for 10 years. First question is, how much money will the account be worth if compounded quarterly? And what about monthly? And then what about daily? So it's 3 questions in part A. So this first thing about compounded quarterly. What does it mean for it to be compounded quarterly? Well, that means 4 times a year. So basically every 3 months you get whatever interest you've earned on it. So it doesn't actually give you interest every day. It doesn't actually pay you for once every 3 months. That's what we mean by compounded quarterly. So let's first start with the formula. The formula says A equals to the initial amount 1 plus R over N raised to the N T. So if that's the case, my initial amount was $7,000. I don't know my final amount. That's what I'm looking for. So I'm going to call that A. And it's going to be multiplied by 1 plus my rate is 5%. 5% is a decimal. It's 0.05. So I know that should be 0.05 over my number of times a year. Well, compound quarterly means 4 times a year. Raised to the I'm running out of space. Let's make it down here. This says A equals 7,000, then 1 plus 0.05 over 4 raised to your number of times a year, which is still 4, times the time, and time is in years, so it's 10 years. 4 times 10. So basically what this is 7,000, and then you can divide 0.05 by 4, figure out what that is, and add 1 to it. We'll figure out what that is now. So you add those together as 1.0125 raised to the 4 times 10. Let's go call it 40. So this is what it is. This is an expression you can plug directly into your calculator. When you plug it in, this is what you come up with. So it's $11,000, $11,505 at about 34 cents. So this is about, because we estimated it. And that's what A equals, the final amount equals. So, so in about 10 years, that $7,000 would have grown to about $11,500, roughly. So it's pretty decent if you can get that kind of return on an investment or a bank. Anyway, let's go to another question. The next question says, what about monthly? So in this case, it's instead of being 4 times a year, it's 12 times a year. So I need to erase this. So if you need it, I copy it down. I'm going to erase this space. So going back to our formula, A equals the initial amount times 1 plus R over N raised to the NT. And I'll write that for them every time. It helps them memorize it. And this time, you can consider all the same variables, but in this case, it's compounded monthly instead. So what we have is, we don't know our final amount, but our initial amount is 7,000. It's going to be 1 plus 0.05, that's my rate, over 12, because every month is 12 months in a year. And it's going to be 12 times 10 years. So this is now 7,000 times 1.004166667. And that's raised to the 120. Because 12 times 10 is 120. So I can plug that directly into my calculator. And this time we get not much of a difference. It's $11,529 and about 7 cents. So you think you got to compound it more often, you get a little bit more money. Yeah, you do. It's not very much more money though. All right, last one is daily. So let's look at that. You know, before I explain it, how about you try it on your own? So let's consider it being done daily. And of course, you know, it's 365 days in a year. So it's 365 times a year. So you actually try this and see if your answer matches mine. All right, so for daily, you should now have 7,000 times 1 plus 0.05, because again, it was 5%. That's why we keep coming up with this 0.05. We started off with 5%. And that was 365 days a year. So it's 365 times 10. You may want to make sure you plug in, that's in calculate properly. Like, if you plug it in that way, you're probably going to get the wrong answer. You should plug in parentheses if you get an assist on using them both separately. And you plug it in, you should get about 11,540.65. About. So it's about $11,540.65. So even then, compounded daily, you get more money. But if you think about it, it's not that much more money. It's not that big of a difference, but it is a different number. All right, so that is the compounded periodically formula. As the second question says, what do you notice about the amount of additional money you make as the frequency of the compound interest increases? Well, we just pointed out is if you compound it more frequently, the amount of money grows faster over time. Or grows to a bigger amount. Next question, different formula. All right, this one deals with continuously compounded growth or decay. So still A is your final amount. And depends on what book you're working out of. This could be a P again, but in this book, it's going to be A sub 0. A sub 0 or A naught is your initial amount. Or the amount you began with. Or beginning value at the beginning. So either call it initial amount or value at the beginning or value at the start. E is just E. It's about 2.71. A lot of other numbers. R is still rate. T is just time. It's not really a number of times a year. It's just time. It could be in days, hours, seconds. It depends on how time is given or whatever, but it's just whatever time it is. All right, so now let's actually put it to use. I'll get this copy down if I were you. I'm about to erase the screen and actually put up new examples. All right, so in 2000, year 2000, the population of a country was approximately 6.25 of 26 million, and by 2081, it is projected to grow to 15 million. Use the exponential growth model here. A equals A sub 0, A naught, E raised to the KT. Sometimes R is written as K. So it depends on who the author is. Sometimes the R is a K. So don't let it freak you out. It's the same thing. It's the rate of growth or rate of decay. in which t is the number of years after 2000, to find the exponential growth function that models the data. So here's a data chart for you. You want to project what's happening later, which is really great. So the first thing that comes up with the formula. The formula we're beginning with is A equals to A naught E raised to the KT instead of R, same thing. So let's just see what we know. What we know for certain is our initial amount. So we know the amount at the beginning, 6.26 million. So since this is in millions, we'll leave it as that instead of making some huge number. It's going to be E raised to the power of K. I do not know its growth rate, but I do know the time. It goes from 2091 from 2000, so it goes 91 years. So this formula is meant to project out 91 years. And I know my final amount. I want to know when it actually makes it to 15 million, so I know my final amount is 15 million. So this is the equation. It says come up with a model for it, as in you want to come up with an A equals equation where there are no variables on this side. Every variable has been figured out. So we got mostly no variables. Only variable over here is K, because remember E is a number. It's 2.71. So only variable there is K. So our goal is to solve that equation for K, which is pretty awesome because we've been solving these equations using logarithms for a while. My question is, how can we get K down for being an exponent? All right, so you take a log of both sides. So let's first go and isolate K. So given that equation, 15 equals to 6.26 e to the 91k. I can divide both sides by 6.26. And what we have now is 2.3962. I estimated that the 4 decimal spaces. So anyway, there's always going to be an estimation. So 4 is good enough. Equals is about e to the 91k. And if I want to figure out how to get k down, I'll take the natural log of both sides. So natural log of 2.3962 is about the natural log of e to 91k. Now we learned a little bit about natural logs. We know that this base here is e. So essentially what happens is they cancel. So this just goes away, leaving you with 91k or about. And this is whatever the natural log of this is. Natural log of 2.3962. I'm going to stop estimating for now. I want to get my answer as accurate as possible, so I'm going to leave it as that. And to solve for k, you divide by 91. So k is equal to the natural log of 2.3962 divided by 91. So it's estimated now. So you plug that into your calculator. K is roughly 0.0096. And that's good enough. That's 4 decimals, so that's pretty accurate. So that's roughly what k is. We can change it to a percentage, but if they ask for it, they ask you to figure out what this formula would be, so you can make any other prediction at any given time. So basically what we have is A is equal to the initial amount, 6.26, E raised to the 0.0096 times 91. Hope you can see that. Right? Yeah, that's what it is. So if I had a different time, whatever, I can plug in a different time. So you could call that 91t. You could actually call this 6.26 E 0.096 t. That way, if I want to figure out any given year, I can make a prediction with any given year using that formula. I just plug in whatever the year is after 2000, and my output should give it to me there. All right, so I'm out of time, but the second part says, by which year should it reach 12 million? I'll let you find out. Go ahead and find out what that year is. But we'll talk about it more in class. That's all the time I have for there. That's all time I have. Good luck.